All right, we are continuing in Rosen, section 1.3 on logical equivalences. And we are going to show how you can use these, the logical equivalences that we've seen in prior slides, these identities, and show how two different compound propositions are equal. We could already do that with a truth table, and in some cases it's very efficient to do that. But in other ways, it can be very instructive to try to do it by a sequence of, or a series of logically equivalent statements. And the way that works is if you have two compound propositions, A and B, we want to be able to start with A and then replace things inside of A bit by bit using the identities from the prior pages so that we end at B. And it looks something like this. We start with A and we replace it with, or some of it, with using the identities to get A1, and then we usually have some kind of justification off to the side for each step. And then we replace A1 with A2 using another identity, and then eventually the last replacement gives us B, and so we'll have proven the logical equivalence. And it's important to keep in mind that whenever you're using these identities, they're often expressed in atomic propositions, but those really are just placeholders for potentially very complicated compound propositions. For example, when we have P implies Q, and we know that it is already know that it's logically equivalent to the negation of P or Q, if we see an implication and the left-hand side happens to be a very complicated compound proposition, as long as we block replace these with those exact compound propositions, we're fine to do the replacement. And the same would go for the other argument in these compound propositions, in this identity. All right, well, let's try one. Here we have two compound propositions. I want to show that they are equivalent. And one of the strategies to keep in mind is, well, when you're starting with one, keep your eye on the other because you want to select identities that will take you in that direction and not diverge. Okay, so we'll do the first line of this, and you can see that we have a negation out front of a disjunction. So we're going to use De Morgan's law to replace that compound proposition with a negation of both sides of a conjunction. So the disjunction becomes a conjunction with both arguments negated. And then we're going to look at that negation right there, and we're going to use De Morgan's law to, to bring it inside and make the conjunction in the right-hand parentheses a disjunction with two negated arguments. And the next thing we're going to do is we're going to target this double negation, get rid of it using the double negation law. And I'll pause here to note that we justify every replacement. That way I can tell what you're doing, you can tell what I'm doing. It's what we've done so far as we've used De Morgan's law and De Morgan's law and double negation. Now what do we want to do next? Well, one thing we might do is we could use the distributive property because we have a conjunction over a disjunction. So let's use the distributive property next. And then that way we basically distribute this negation of P into that disjunction. So we get negation of P and P, or the negation of P and the negation of Q. Well, we know that this is going to be false by the negation law. And here we just we just basically wrote down the identity that allowed us to make that substitution of F. And we also know that F or anything returns anything by the identity law. But there's a step here, and it's also in the book, that's kind of extraneous. All it does is switch these two arguments using the commutative law. And that's fine because the truth table that we did for the identity law had the F on the right, so that's fine. But it's not absolutely necessary. And now because of the identity law, then this will just return the left argument. And we've proven that these two compound propositions are equivalent because we've justified every step, and we could go backwards or forwards with this approach. All right, let's do one more. We want to show that this compound proposition, P and Q implies P or Q, is a tautology. In other words, that it is always true. All right, well, the first thing we're going to do is, because this is an implication, we're going to use that identity that we've learned, that an implication can be replaced by the negation of the hypothesis disjoined with the consequence. And the justification here was truth table for implication. Table 7, I believe it's called. All right, so there's the first replacement. We want to show that it's always true. The next thing we're going to do is De Morgan's law on that negation sign. And now notice that we have a sequence of disjunctions. If I've got a sequence of disjunctions, I can do those in any order I want by the associative law. And so I'm moving those around, and in the commutative law as well, to get the negation of P disjoined with P and the negation of Q disjoined with Q. Well, by the negation laws, those become true. And I'm going to mark this out and say that's the negation laws, because that's what we called them in the earlier slides. And then we have a couple of different things we could apply to get this down to true, and we're going to use the domination law for T. And so we've proven that this compound proposition is always true. Okay.